I would like to start by thanking the organizers for giving me this opportunity. So this is my third time here at ICTS, but yeah, first time at this end of the auditorium. So I'll be talking about complementary signatures of alpha attractor inflation in CMB and gravitational waves from cosmic strings, which is based on the work which is supposed to appear next week. This work was done in collaboration with Anish, Ghoshal and David Mota, and I am a master's student at IISER Kolkata, and a significant part of this work was done at HRI. So I will start by giving you a brief overview of what topological defects are in the context of cosmology. Then I would explain how the gravitational wave background from cosmic strings look like, and I will explain what the standard scenario implies. Followed by, I will explain the impact of inflation, which is a non-standard scenario, the impact of inflation on cosmic strings, and how it subsequently affects the gravitational wave spectra in that scenario. Then I will discuss a bit about the complementary relations between CMB and gravitational detectors with the help of cosmic strings, and then I will summarize. So starting off, consider the spontaneous breaking of a Z2 symmetry in the context of a real scalar field theory. The potential V phi is free to the potential V phi, as you can see, respects the Z2 symmetry, and after a phase transition has taken place, the scalar field phi is free to settle in either this vacua or this vacua, denoted by plus V and minus V, and these different vacua are placed randomly on the physical space and are of length scales greater than the causal horizon. So these different domains, plus V and minus V, are separated by what we call the domain wall, and in going from one vacua to another, you need to cross this domain wall. If you look closely, you would realize that at the center of the domain wall, which is essentially a surface at phi equals to 0, the Z2 symmetry is still preserved. So it's a property of the domain wall to preserve the underlying symmetry at its core. Now we can extend this argument to say two real scalar fields and ask the same question, that where in the physical space is our U1 symmetry now preserved? So the answer would be at the intersection of these two surfaces where the fields individually go to 0, which and the intersection of the two surfaces is essentially a one-dimensional object, which is our cosmic string. And similarly, one can do this for a monopole as well. So a more elegant description is given in terms of the homotopic group of the vacuum manifold. So if you have a non-trivial homotopic group, topological defects would be present in a vacuum manifold. In particular, for cosmic strings, your vacuum manifold must have holes in them, or in other words, non-contractible loops must be present in the vacuum manifold. So what's special about cosmic strings? Cosmic strings, unlike other defects, has this unique ability to intercommute, which means it can cut and chop each other as well as itself to form loops, which later on would radiate gravitational waves. And this is an equation that captures all these dynamics. Anybody who works on cosmic strings must be familiar with this equation. And this is a full numerical spectra, full numerical simulation of the gravitational wave background from a local cosmic string. So as you can see, the string tension G mu controls the amplitude of the spectra, and as we go down from 10 to the minus 13 to 10 to the minus 17, the amplitude decreases. A better way to understand what's happening is through this analytical approximation of the gravitational wave background, so gravitational wave spectra. The blue dotted lines represent those cosmic string loops that are formed during the radiation era and started emission right away in the radiation era. The green ones represent those loops that were formed during radiation era but started emission in the matter era, and the red ones represent those loops that are formed later in the matter era and started emission in matter era. So all this is a very well established fact. This is a standard scenario where cosmic strings are formed due to a phase transition that has happened after inflation. All right, so what if we take the scenario where cosmic strings are formed during inflation, and there has been several string-inspired inflationary models that suppose the fact that cosmic strings could be formed at the later stages of inflation or at some point during the inflationary epoch. So in order to understand this, there are two important ingredients. First one being the turning point frequency, and the second one is our inflation model that would drive our early universe expansion. So for now, let's trust me and take this equation for the turning point frequency. An important point is the turning point frequency depends on something called the TRE, which is the re-entry temperature. It will become clear in a moment what it means. And the re-entry temperature is dependent on the energy scale of inflation. But the energy scale of inflation cannot take any random value because it depends on the tensor to scalar ratio R, which is constrained to less than 0.036. So the next important ingredient is our inflation model, and we stick to alpha attractors. There are the most important models are E model, the T model, and the polynomial attractor. For now, let's stick to T model of inflation, D model of alpha attractor. And these are the NSR predictions for the T model with n equals to 1. These are constant alpha contours. And the next, there's one more thing that we need to understand, which is the velocity one scale equation. So these are essentially coupled differential equations, which depends on the correlation length L and the mean velocity of the cosmic strings, V bar. K V bar is essentially a phenomenological parameter, which we call the momentum parameter and measures a deviation from a straight string. So K V bar equals to 1 represents a straight string. Yeah, so we will look at this equation because this is the important equation in the context of our study, and particularly in the first term, h times L. So HL describes the characteristic length. HL describes how the characteristic length is impacted by the expansion of the universe. And there are two scenarios which we will look into. During the inflation, HL is much greater than 1, which implies that the strings are effectively frozen in their co-moving coordinates and cannot undergo intercommutation. But later on at some point, when inflation stops and we have our standard cosmological evolution, we will have HL equals to 1, and that's when intercommutation starts and we have our late time evolution. And here for n greater than 2, the Hubble horizon will eventually catch up and the string with the string length, allowing them to re-enter and initiate loop production. This is where the re-entry temperature comes into picture. So with all this, using all these things, we can plot the stochastic gravitational wave background spectra in this non-standard scenario where the cosmic strings are affected by inflation. So as you can see, depending on the number of NCS is the number of e-folds of inflation that our cosmic string has experienced. And as the value of the NCS goes down, we can see the turning point frequency shifts towards the right in the ultra-high regime. One can play around with so this is for R equals to 0.022, and we can reduce the energy scale and see how it varies. So essentially, as we decrease the energy scale of inflation, the maximum permissible value of the NCS, which is the maximum e-folds of inflation that our string can experience, decreases. And similarly, if we reduce the string tension in a similar manner, the NCS value also decreases. Now, the next thing is to find a relation between the tensor to scalar ratio and the turning point frequency. So you have seen these three equations, and upon doing some simplifications and playing around, we end up with the tensor to scalar ratio R as a function of the turning point frequency. Now, I've already told about NCS, and as you have seen that G mu controls the amplitude of the gravitational wave spectra, and we consider the following three observatories where our turning point frequency would lie. So we consider the polynomial attractor with n equals to 1. This is how our inflation potential looks like, and we consider F delta for now to be within the working range of the square kilometer array. These are the working frequency range, and now the name of the game is to find all possible values of NCS that satisfies all these conditions. And in doing so, we see this shaded region, which essentially tells us all those NSR values associated with NCS that can produce potentially detectable gravitational wave signals at the SK observatory for strings of string tension 10 to the minus 13. Any NSR value outside this shaded region are unable to produce detectable gravitational wave signals from cosmic strings of string tension 10 to the minus 13. Yeah. So we have done this analysis for LISA and DESIGO as well, and we are able to constrain the spectral index to the following values, and well, we can play around and check for different inflation models. So due to the lack of time, I've done this for polynomial attractors, but you can extend this argument to the T models as well. So yeah, I will leave you with the summary and conclusion. But before that, I would like to acknowledge my master's advisor, Anshuman Maharana and Francisco Muia, with whom I started working on this, and to Yvonne, Divya, and Swagat for fruitful discussions over the last few days. And thanks to HRI for their support. Yeah, so this is one of the pictures. Like, this is where I used to sit in the morning to catch my supervisor. So yeah, thank you. Yeah.
Thanks, Mainak, for the wonderful talk.
Yeah.
As you change reheating equation of state and duration, NS would shift forward.
Yeah, shift. Yeah, we have considered instant reheating. So
that's fine then. Yeah. But 65 is not correct for instant reheating.
Okay, so yeah, okay, maybe I will take a look into it later.
Okay, any other questions? If not, thanks.
Oh yeah,
one.
Okay.
I can just hear.
Oh.
So, this is very, very nice. Usually in PTA analyses, one of the things we've been doing is we've been saying that the consistency relation needs to be broken for string searches in PTAs to make sense. So I'm not sure if that needs to be done for what you just presented. I wasn't able to follow that.
I actually didn't get your question, so maybe we can.
In PTA analysis, if you look at the NANO-Grav and the ePTA paper, which I think are the only places where the PTA groups have searched for strings or backgrounds from strings, we say that the consistency relation does not, we break the consistency relation, otherwise we won't end up with the blue tilt we need to search for these things in our data. I mean, it's just, we're just playing a game with this thing, right? So I was not sure, when I see the spectra from you, I'm not sure if that needs to be done or you can produce backgrounds which are consistent or which can be tested by PTAs without breaking the consistency.
Maybe I'm not sure, maybe Anish can address that.
Okay, thank you once again. So